Hi guys, so today we are going to talk about quantum numbers. So that's the topic. And just to introduce you to this Schrodinger wave equation. This is the equation that kind of narrows through its solutions the location of an electron in an atom. So every electron, every atom has a certain number of electron based on the atomic number. And those electrons are located in different places inside an atom. And the solution, the answer to this equation, basically will give us the information where a certain electron is in an atom. Okay. Um, this equation has four answers. Okay. These four answers are the four quantum numbers, and knowing these four quantum numbers, we can narrow down the position of an electron inside an atom. So that's what it is about. We're going to describe these numbers, and then we're going to see how they connect with each other to give us that location of the electron inside an atom. The first number that we have is called the principal quantum number. The principal quantum number, the symbol is N, and it is pretty much the number of the energy levels an electron can be in, basically. Is the same number that we saw when we talked about the Bohr's model. Okay, that's the same number. So N, the principal quantum numbers, can have values, integers, between 1 and 7. And why is that? Because the biggest atom that we have in the periodic table right now can have up to 7 energy levels. So the electrons can be in up to 7 circles around the nucleus, basically. And if you pay attention to, there's a very good correlation between the periodic table and these quantum numbers, the way they're going to be laid out. There are 7 periods in the periodic table. The atoms belonging to a certain periods have a certain number of energy levels equal to the number of the period. So all you have to do is look in the periodic table for your atom, and you're going to see how many energy levels the electrons have can have in that particular atom. So N stands for energy levels, the energy circles that the electron can be in a certain atom. We have a formula that allows us to calculate the number of electrons that we can put in an energy level, and that doesn't mean the minimum number, it means the maximum number of electrons. So if energy level N is 1, the formula reads 2 times 1 squared equals 2. So you put 2 electrons on the first energy level. The smallest circle, the closest to the nucleus, is the lowest in energy, is the most stable one. That's why it's like a VIP location for the electrons. Everybody that has electrons, all the atoms, will shove their first electrons in the first energy level. But that energy level is very small and can only hold 2 electrons. What about hydrogen that has 1 electron? Well, it can hold up to 2 electrons. You can have 1 and you can have 2, okay? And that is the end of the first energy level. There are no more electrons than 2, but it can be less than 2. If you look at the second energy level for N equals 2, 2 times 2 squares, 2 times 4, that's 8 electrons. So the second energy level is a little bit bigger and can hold up to 8 electrons. So if an atom has 3, 4, 5, up to 10 electrons, the first to go in the first energy level, and then with the third, you start populating the second energy level, and you go up to 8 electrons in that level. And it goes the same way. So the third energy level can have maximum 18 electrons, 2 times 3 squared, 2 times 9 is 18, and you can calculate from there on. So this is the maximum number of electrons that can be put in an energy level. The trick is to remember that an electron, when the electrons populate an atom, they cannot go on a higher energy level if the underneath levels are not completely occupied with electrons. So you cannot have electrons in the second energy level unless the first energy level is completely full. You cannot have electrons in the third energy level unless the first and the second energy level are completely filled with electrons. So the energy levels show up in atoms. The bigger the atom is, the more energy level it has. So the way you increase by increasing the value of this N, you increase the size of the atoms in reality. Good with that? Now, the second quantum number is called the angular momentum quantum number. It has a fancy name. The symbol for it is L. And the electrons are on energy levels, but they don't just sit there and they float around in an energy level. They are basically put in atomic orbitals. And when we talked about the quantum mechanical model, we said that an electron belongs in an orbital, like a three-dimensional fuzzy space around the nucleus, okay? So every energy level has its own set of orbitals, fuzzy clouds. And by associating this L to an orbital, we basically find the kind of, if you imagine the atom like a town, which has circular streets around the nucleus, basically around the center, and in each circle, in each energy level, you have different type of housing. These orbitals will be like different type of houses that you have where the electron will go in. So if you see a value of L of 0, that is always an s orbital. What is an s orbital? Is a spherical cloud that is in the center, that can hold the electron. A spherical cloud of energy, three-dimensional, okay? That is, so you have to find this association to kind of connect the letter S with the number for L. An L equals 0 is always the symbol for an s orbital. An L equal 1 stands for a p orbital. A p orbital is another three-dimensional cloud, but it has the shape of a dumbbell, and it has a little bit of higher energy compared to the p orbital, to the s orbital. For L equals 2, we have the d orbitals, okay? The d orbitals are even more complex in their shape, looks like a clover leaf, and they have a higher energy compared to the p orbitals. So the energy of the orbitals increases as you move from s, going to p, going to d. The last one that we talk about, L equals 3, indicates the existence of an f orbital. So if an electron has a quantum number, an angular momentum quantum number, L equals 3, that means that electron is in an f orbital. If an electron has a quantum momentum L equals 2, that means it belongs to a d orbital. So by knowing this secondary number, this second quantum number, actually we know what kind of cloud, what kind of orbital the electron belongs to. Good. That is in an energy level. Okay? So the energy of the orbitals increases from s up to f. Okay, every orbital has its own shape and its own energy. Okay, so keep that in mind. Now, what are the values that we can have for L? We saw 0, 1, 2, and 3. Let's look at the values that L can have, because the values of L depend on the value of N. So we have the principal quantum number, hold on, and that will dictate what kind of values of L can I have. So if your N, you have your N that goes from 1 up to 7, every integer, right? Now based on this N, I have to calculate what values of L it allows me. And the L is always calculated, it goes from 0, taking all the integers up until n minus 1. Up until n minus 1. So L goes from 0, all the integers up until n minus 1. So it depends on M, on n. This is an example. For n equals 1, first energy level, L can be 0 and can be another integer that equals to n minus 1. What is the n minus 1 in this case? 1 minus 1 is 0. So it's just 0. There's no other option. But for n equals 2, that means your L can be 0. And also, 2 minus 1 is 1, right? N minus 1 is 1 in this case. That means L can also be 1. So in this case, in the second energy level, I have two types of orbitals, because an orbital L equals 0 is an orbital s. Here I have an orbital s and an orbital p, if you think about it. So on the second energy level, I can have two types of orbitals, two types of fuzzy cloud that can hold my electrons, s and p. If your n equals 3, on the third energy level, I have L equals 0, L equals 1, and 3 minus 1 is 2, right? So I can go up to L equals 2. So I have three types of orbitals, S, P, and D, if you think about it, that are allowed to exist on the third energy level. For n equals 4, I have L equals 0, L equals 1, 2, and 3. So I have all the orbitals S, P, D, and F. And it goes like that. So for n equals 7, I can have values of L from 0 up to 6. But when in the previous slide, when we talked about the clouds, the orbitals, I said we have L equals 0 S, then P, and then D, and then F for L equals 3. So where are the other values of L? What do they represent? L equals 4 and 5 and 6. Are they orbitals? Yes, they are. The big, complicated, high energy orbitals. So far, the periodic table does not have those elements that have so many electrons to be able to place them in those kind of orbitals. So in reality, so far in the periodic table, the electrons can be put in orbitals S, P, D, and F, and that's it. The orbitals that come after that, for L equals 4, we have orbital G, and then orbital H, and all those orbitals that we have 3 more type of orbitals that come from this value n equals 1, n minus 1. Those are orbitals that are not populated. It's like big mansions waiting to be populated with electrons if we have those kind of atoms that have that many electrons. Okay, so they exist, but they're not useful for us in terms of what we discussed here. Okay, so now let's look at this situation. I'm going to draw a little bit of a chart here. So if I have my nucleus in the middle, okay, and I have energy level number 1, n equals 1, and in energy level number 1, the only type of orbital I have is orbital S. I'm going to just put it here as an orbital S. Then on energy level number 2, n equals 2, I can have orbital S, and I can have orbitals P. Cool. On energy level number 3, I can have orbitals S, orbitals P, and then orbitals D. And then on the 4th energy level, n equals 4, let me put it here, I can have orbitals S, the P orbitals, the D orbitals, and the F orbitals, which are the complicated ones. So starting with the 4th energy level, I can have all type of clouds, all type of orbitals present, available for electrons to populate. Okay, now I want you to notice this. I have orbitals S in the 1st energy level, in the 2nd, in the 3rd, and in the 4th, and in every energy level, because L equals 0 is always present depending, it doesn't depend on the value of n. So to me to be able to differentiate from the orbital S from the 1st energy level to the 2nd to the, I have to put a number of the energy level in front of it. So this would be 1s, this would be 2s, 3s, 4s, and so on. So here it's not just s, it's 1s, it's 2s, 3, and 4s. So by putting the value of the energy level, well, the other way around, right? This is 1, this is 2, this is 3. By putting the number of the energy level in front of the orbital, I turn just a simple orbital into what we call a sublevel, because it tells me that this S orbital belongs to the 1st energy level. So it's a sublevel 1s in the 1st energy level. For the 2nd energy level, I have the 2s and the 2p. So on the 2nd energy level, the 2nd circle, I can have orbitals 2s and 2p. So there are 2 sublevels in the 2nd energy level. On the 3rd energy level, I have 3s, 3p, and 3d type of orbitals. So 3s, 3p, and 3d sublevels. So by attaching a number in front of a letter, I'm indicating where, on what energy level that particular orbital is located. And that turns into being called now a sublevel instead of just an orbital. Good? So far? Okay. So an older way to say it, instead of energy level, people used to call it shells. And instead of sublevels, they call them subshells. So shell 1, 2, 3, up to 7, and then the subshells, 1s, 2s, 2p, 3s, 3p, 3d, whatever the situation may be. Good with this? Okay. Now, let's look at a quick application of this. If I say I have an electron that has this following quantum numbers, n equal 3, L equal 2. I want you to give me the sub-level where this electron is located. What sub-level is it located in? Well, the first number gives you the number in front, and the L equals 2 is always associated with an orbital D, correct? So 3D is your sub-level. So your electron that has these two numbers, the first two quantum numbers, these two, it's in a 3D orbital, in a 3D sub-level, okay? What if I say, I have an electron in a 4F sublevel. Give me the two quantum numbers associated with this electron that is in this sublevel. So the first quantum numbers comes from this number, n equals 4, and the second quantum numbers come from the value of s. F orbitals means L equals what? 3, correct? So always, what I want you to remember is that orbitals S have a value of L equals 0, and this is set in stone, this doesn't change with anything. If you see an L equals 0, you always talk about orbitals S. If you see an L equals 3, you always talk about orbital F, and you should be able to flip-flop from the number to the letter automatically, okay? So you're gonna see two types of questions here. First, when I give you the sub-level and I want you to pull the quantum numbers from them. Second is when I give you the quantum numbers and I want you to pull it in the form of a sub-level. Those are the only two things that you're gonna see. Oh, one more thing. I want you to pay attention where some orbitals pop in for the first time. In the first energy level, you don't have a 1p orbital. You don't have a 1d orbital. So in the first energy level, it's just 1s. So the first p orbital is the 2p. So it comes in the second energy level. The first d orbital is in the third energy level. The first f orbital is in the fourth energy level. So a denomination as a 3f, a sublevel 3f doesn't exist, is incorrect. So if I give you n equals 3, L equals 3, these two quantum numbers are not correct. Because L equals 3 doesn't exist for n equals 3. Because for n equals 3, L stops at n minus 1, 3 minus 1. The maximum L is 2. Get it? So some denominations, that could be another type of question. What denomination of a sublevel is incorrect? And I can throw something like 3f or 1d or whatever. Just remember that not all the orbitals show up in the first energy level. They show up in different energy levels. So anything less than 4f is not possible. Anything less than 3d is not possible. And anything less than 2p is not possible. The only one that shows up in every single energy level is the orbital s. You have 1s and you have 7s all the way, okay? Go with this? Okay, so n, the first number, is like the street. L, the second number, is like the type of houses, right? Now each house can have different rooms. So let's talk a little bit more about the third quantum number. So the third quantum number is based on L. It's a number that pins on L, basically. So the first number, n, was independent. Then n generated your L. Now L generates the third quantum number. So the third quantum number is called the magnetic quantum number. The magnetic quantum number. And basically it tells you that every orbital that you have, s, p, d, and f, can have different orientations in space. And whether it's on the OX axis, or it's on the OY axis, or it's on the OZ axis, or in between the axis, all those orientations are given a certain number, okay? So the M, the symbol for M, so let me erase here. So if you have the third quantum number, the magnetic number, the symbol is M, or sometimes you're gonna see it as M subscript L, because it's based on L, okay? So there are two notations, just M or just M subscript L, okay? This is the magnetic number, and it has values from negative L all the integers including zeros up to plus L. So if for the s orbitals, if you think about it, if L equals 0, what values can M have? I told you that it's based on the values of L. M can go from -0 to +0, all the integers, which is nothing else but 0, right? So M equals 0. So basically, and these are not, this is not math necessarily, these are more notations than anything else. When M equals 0, meaning one value for M, or the orbital S, means that the orbital S can have just one position in space, and that is because he's a sphere, is going to be in the center of the axis. And it doesn't matter how you switch that orbital S in the center of the axis, it's going to be basically the same thing. You rotate the sphere, it's not going to change, it's going to be in the center. So you only have one value for M. It doesn't matter if that value is 0, that is just a notation. Remember, it's just one value for S. So the type of orbital S, it shows up in one single position, basically. It's one value for M, okay? And we normally show this type of orbitals with, when we want to draw the representation, when we want to draw the diagram, we show it with a box or sometimes just a line when we simplify things. So one box, this is your orbital S, and this is the M equals 0 value. It's like a label M equals 0, but it's just one box because M has one value, okay? Now if you look at the orbital speed, for the orbital speed, you have L equals 1. For this L equals 1, if you want to look at the values, the possible values of M goes from -L to +L. So from -1 to +1. What integers are there? -1, 0, and 1, right? So I have 3 possibilities, and so that for me is showing the orbital L with always with 3 possible boxes, with 3 boxes. This is your orbital P, and this is box number -1, this is box 0, and this is box 1. And why is that? Because an orbital P is like a dumbbell, right? So if you take the axis and you're gonna start rotating the orbital around the axis, on the OX axis you have this, which is L equals -1. On the OY axis you have this one, which is the other value of M, L equals 0. And on the OZ axis you have the third orientation. So you flip the orbital in space around the axis, and you have this with a quantum number M as 1. So these are the 3 possible rotations in space that gives you these 3 values of M, that gives you 3 positions for the orbital. Okay, so that's why the orbital P always shows up in a set of 3, because it has these 3 options of being in space at all times. Okay, so orbital P comes in a set of 3. These 3 orbitals, these 3 positions, gives me orbitals that have the same energy. So these 3 boxes contain electrons that have the same energy all the time. Okay, so that is the situation with the p orbital. The d orbital, remember, it's a clover leaf, so they're more complicated, but we can do the same reasoning for the d orbitals. L equals 2, so M can go from -2, -1, 0, 1, and 2. And these are 5 values. By the same reasoning, I can draw an orbital D as a set of 5 boxes. This is box -2, this is box -1, 0, 1, and 2. So my electrons can be in any of these positions, in any of these boxes. Okay? So, and then for L equals 3, for the F orbitals, L equals 3, I have the values, possible values of M will go from -3, -2, -1, 0, 1, 2, and 3. This is a total of 7 values. So I'm going to draw an orbital F with a set of 7 boxes. And this is box number -3, -2, -1, 0, 1, 2, and 3. Okay? So this is the situation with the orbital. So anytime you have to draw or to think about these orbitals, think of them as being in sets. Just the orbital S has one orbital, one box. All the others come in sets of 3, 5, and 7, okay? And now every little box is its own orbital. Its own orbital. It's the orbital in a certain position, in a certain location in space, rotation in space. And every orbital can be populated by 2 electrons. That's what we said at the beginning. In every box, I can put 2 electrons. So if you think about it, how many electrons can an S orbital hold? If I put 2 electrons here, this is 2 electrons. One box, 2 electrons. Here's 3 boxes, 3 times 2 is 6 electrons. Here's 5 boxes, 5 times 2 is 10 electrons. And here is 14 electrons. 7 boxes times 2. Every orbital can hold the number of orbitals times 2 electrons, okay? The number of boxes times 2 electrons. That's the maximum number of electrons that you can put in these orbitals. Can you put less? Of course, but not more than that. So never try to put 3 electrons in an orbital S, or 7 or 8 or more than 6 in an orbital P, or more than 10 in a D, and more than 14 in an F orbital, okay? Now, these electrons that go in an orbital, the 2 of them, have to spin in opposite ways, in opposite direction. One spins clockwise, the other one spins counterclockwise. The direction of this spin is given to you by the 4th quantum number, okay? So the first 3 numbers are N, the energy level, L, the orbital, M, what's inside of an orbital, how many boxes, how many orientation in space the electron can have, the orbital can have. And the last number is your spin number, which is symbolized as an S or MS. Describes the spin, the rotation of the electron inside of an orbital, inside of a box, okay? So when we symbolize an orbital, hold on, let me get to the picture. An electron is symbolized as an arrow. If I draw an arrow with my arrow tip up, that is the symbol, of an electron that has the spin plus 1/2, not plus 0.5. Remember, these are notations. It has nothing to do with math. Plus 1/2 is the notation for an electron that spins clockwise. And the negative 1/2 is the rotation of an electron that spins counterclockwise, okay? And the symbol is the arrow down. So if I am to put, and this is the thing, when you put electrons in these boxes, in these orbitals, basically you cannot put the electrons to have the same spin in the same box. Because there is a principle called Pauli's exclusion principle that says an electron, 2 electrons in an atom cannot have the same set of 4 quantum numbers, cannot have the same numbers, the 4 numbers. They can have 3 that are the same, but the 4th one is always different because the spin is always in opposition. One is plus, one is negative, 1/2. So I know the notation is, the spin is S, but some people call it MS, like this, right? Don't ask me why. This is another notation for the spin. We have the ML for the M, the first M, the magnetic number, the 3rd number, and now we have spin or MS, because the spin, and the spin can be 2 numbers, plus or minus 1/2. Plus 1/2, you show it like this, electron, negative 1/2, you show it like this. So when I am to populate the electrons in orbitals, always show 2 electrons in a box, maximum 2 electrons in a box, with arrows up and down. So here I can put 6 electrons, here I can put 10, and of course here I can put 14. Good? So the 4 quantum numbers, N, the principal quantum number, tells you the energy level. L, the cloud, the orbital, the secondary quantum number, tells you what kind of orbital the electron can be in a certain energy level. The third number refers to what's inside of an orbital, okay? And that magnetic number is showing the orientation in space of that orbital, and can have different values based on the value of L. And that generates the sets of orbitals that have the same energy. And the fourth number can be plus or minus negative, plus or minus 1/2 is the spin number that tells you how the electron rotates inside of an orbital. Like having houses on the street, the orbitals. Inside the houses, you have rooms, the boxes, and inside a room, the electrons can be this or this. Okay, that's pretty much the way you look at these 4 quantum numbers. And now we're gonna do some applications with it, okay? So, Liz, cut it off.